Gaze out into the vast, dark expanse between the stars. What do you see? Your eyes tell you there is nothing there, just an endless, silent, and empty void. For centuries, this is what we believed. That space, true empty space, was the ultimate definition of nothingness. A perfect vacuum, devoid of all matter, all energy, all anything. It was the stage upon which the grand cosmic drama unfolded, but it wasn't a player, it was just the background. But what if our senses, as they so often do, are deceiving us? What if that emptiness is not empty at all? Imagine a perfectly calm ocean surface. It looks placid, still and featureless. Yet underneath that serene facade, there is a world of activity. Currents flow, pressures shift, and the water itself is made of countless molecules, all jiggling with energy. The universe, it turns out, is much the same. The laws of quantum mechanics, our most profound description of reality, tell us a startling story. They say that empty space is in fact a seething, bubbling cauldron of potential. It is filled with a fundamental energy, an energy that exists even at the coldest possible temperature, absolute zero. This is the zero-point energy. This isn't just a fanciful idea or a mathematical trick. It's a direct consequence of one of the deepest principles in physics, the Heisenberg uncertainty principle. This principle states that you can never know both the exact position and the exact momentum of a particle at the same time. If a patch of space were truly empty, with zero energy, you would know both its energy, zero, and its state, nothing, with perfect certainty. The universe simply does not allow this. So even in the most profound vacuum, pairs of virtual particles must constantly pop into existence and then annihilate each other in a flash, creating a background hum of energy that fills all of space. So the next time you look up at the night sky, don't just see the stars, see the space between them, and know that you are not looking at nothing. You are looking at a hidden reservoir of energy, a quantum foam that underpins the very fabric of reality. This discovery changes everything we thought we knew about the void. It tells us that the universe is never truly at rest. It is alive with a fundamental, invisible energy. The question then became, not is it there, but how can we prove it? How can we reach into the nothing and feel something? How do you detect an energy that is everywhere, all the time? It's like trying to weigh the ocean while you're swimming in it. The first real clue, the first tangible hint of this hidden energy, came in 1948 from the mind of a Dutch physicist named Hendrik Casimir. He wasn't even looking for zero-point energy. He was working at Phillips Research Labs, trying to understand the sticky forces between molecules. But his calculations led him to a stunning prediction. He imagined two perfectly flat, uncharged metal plates placed incredibly close together in a perfect vacuum. What would happen? According to classical physics, with no charge and no gravity to worry about, absolutely nothing should happen. The plates should just sit there, motionless. But Casimir saw it differently through the lens of quantum mechanics. He realized that the space between the plates was different from the space outside them. Remember those virtual particles, the quantum foam? Outside the plates, particles of all wavelengths can pop into existence. But between the plates, only particles whose wavelengths fit neatly into that tiny gap are allowed. It's like a guitar string. It can only vibrate at specific frequencies. This restriction means there are fewer virtual particles, and thus less zero-point energy, pushing on the plates from the inside compared to the outside. The result? The greater pressure from the outside pushes the plates together. It's a force from nothing, a force generated by the vacuum itself. This predicted force, now known as the Casimir Effect, was an elegant and profound idea. It suggested that we could, in fact, witness the effects of zero-point energy by creating a special kind of space where its full power was limited. It was a whisper from the void, a clue that we were on the right track. For decades, this effect was incredibly difficult to measure. The forces are minuscule, and you need plates that are almost impossibly smooth and close together. But by the late 1990s, technology had caught up. Experiments confirmed that Casimir's predicted force was real. The plates did indeed move. It was a monumental achievement for physics. And yet, it wasn't the final word. Skeptics argued that other forces, like stray electromagnetic fields or molecular interactions, could be limiting the effect. The Casimir effect was a powerful hint, but it wasn't undeniable proof. We needed a new way to listen, a better experiment to truly isolate the quantum hum of the universe. The Casimir effect was like hearing a faint, muffled sound through a thick wall. You know something is there, but you can't make out the words. It opened the door, but it didn't show us the full picture. To truly confirm the reality of zero-point energy, we needed to move beyond simply measuring a static force between two plates. We needed to find a way to observe the dynamic nature of this energy, the constant bubbling and fizzing of the quantum foam itself. We needed to build experiments that were more sensitive, more direct, and less open to alternative explanations. The challenge was immense. The journey required a complete shift in experimental design. Instead of just using the void's energy to push things around, the new generation of physicists wanted to see it in action. They asked, if this energy is really a sea of fluctuating fields, can we see the waves? Can we measure the random kicks and shoves that these virtual particles give to incredibly tiny objects? This is a much harder task. It's like trying to spot the ripples made by a single raindrop in a storm. But with the dawn of nanotechnology and quantum computing, we finally had the tools to build such exquisitely sensitive detectors. Enter the new era of zero-point energy research. We moved from large passive plates to microscopic active systems. Think of tiny diving boards or cantilevers, so small they are measured in micrometers, or fantastically cold superconducting circuits, where electrons flow without resistance, making them hypersensitive to the slightest energetic disturbance. These aren't just smaller versions of the old experiments. They are entirely new platforms, designed not just to feel a constant push, but to feel the individual random fluctuations of the vacuum energy field itself. It's the difference between feeling the steady pressure of the wind and feeling each individual gust. These new approaches promised a much clearer signal. By looking for the random, unpredictable noise predicted by quantum theory, scientists could filter out the steady, classical forces that had clouded earlier results. If they could measure a random jitter in a micro-cantilever that perfectly matched the predictions for zero-point energy fluctuations, it would be a smoking gun. It would be like finally hearing the words in that muffled sound from behind the wall. The stage was set for a breakthrough, a moment where a theoretical ghost could finally be captured and measured as a physical reality. Let's dive into the laboratory where today, on 30th January 2026, these incredible experiments are happening. One of the most compelling setups involves something called a micro-cantilever array. Imagine a row of diving boards, each one thousands of times thinner than a human hair. In a perfect vacuum and cooled to near absolute zero, these cantilevers should be perfectly still. But, well, they aren't. Physicists have observed them trembling, vibrating with a tiny, random motion. This isn't just thermal jiggling. They are far too cold for that. This is the quantum jitter, the direct result of being constantly battered by virtual particles from the vacuum. The data from these experiments is astonishingly precise. Scientists can measure the frequency and amplitude of this vibration. And when they compare their measurements to the predictions of quantum field theory, the numbers match perfectly. It's as if the universe has a specific hum, and our tiny cantilevers are vibrating in perfect resonance with it. They are acting like microscopic buoys, bobbing up and down on the surface of the quantum sea. This random, unpredictable motion cannot be easily explained away by classical forces, which are typically smooth and predictable. We are, for the first time, directly witnessing the chaotic nature of the void. Another powerful line of evidence comes from the world of superconducting circuits. These are the building blocks of quantum computers. When cooled to just a fraction of a degree above absolute zero, these circuits become incredibly sensitive to the electromagnetic environment. Physicists have found that even in the most shielded, isolated vacuum chamber, these circuits still exhibit a fundamental level of noise. There's a faint, ever-present crackle of energy that affects the quantum bits, or qubits, within the circuit. Where is this noise coming from? It's the zero-point energy of the electromagnetic field itself. This effect, known as the Lamb shift, was first predicted in atoms, where the vacuum energy slightly nudges the energy levels of electrons. Now we are seeing the same principle at work in our own engineered devices. The energy levels of our artificial atoms, the qubits in our superconducting circuits, are being measurably shifted by the seething energy of the vacuum. This isn't a force that pushes things. It's an energy that subtly changes an object's fundamental properties. These experiments provide solid, quantifiable data, turning the abstract concept of zero-point energy into something we can measure on a voltmeter. The ghost in the machine is real, and it has an electrical signature. For decades, zero-point energy lived in the shadows of physics. It was a fudge factor in some equations, a theoretical necessity that many hoped would just go away. The Casimir Effect gave it a physical presence, but it was still indirect. These new experiments, with their vibrating cantilevers and noisy circuits, have dragged it out into the light. We have moved beyond inference to direct observation. We are no longer just seeing the shadow of the quantum vacuum. We are feeling its pulse. The data is so clear that zero-point energy is now being treated as a tangible, measurable, and engineerable resource. Think of it this way. For a long time, air was just emptiness to us. Then we learned to feel the wind, which was like the Casimir Effect, proof that something was there. But now, with these new experiments, it's as if we've built a microphone that can hear the individual air molecules bumping into it. We can count them, measure their impact, and characterize their behavior. The zero-point energy has transformed from a mysterious, ghostly concept into a physical force with well-defined properties. It has a specific energy spectrum. It causes predictable, in a statistical sense, fluctuations. And it interacts with matter in ways we can now measure and control. This transition from theory to tangible reality is a pivotal moment in science. It solidifies our understanding of quantum field theory, the bedrock of modern physics. The theory didn't just predict this energy, it predicted its specific characteristics, its flavor of noise, and the experiments have confirmed it. This gives us enormous confidence that our mathematical description of the universe is on the right track. It tells us that the universe is fundamentally a quantum place, all the way down. The classical, quiet, empty void does not exist. Reality, at its most basic level, is a storm of quantum activity. What this means is that empty space is now a physical object of study. It's a medium, not a void. It has properties we can measure, like its energy density. It has dynamics we can observe, like its fluctuations. We can now ask questions that would have sounded like nonsense a century ago. Can we manipulate this energy? Can we harvest it? Can we change its properties in a localized area? The vacuum is no longer a passive backdrop. It's an active player in the cosmos, a fundamental component of the universe's operating system that we are just beginning to learn how to access. Whenever we gain mastery over a fundamental force of nature, technology leaps forward. Mastering electromagnetism gave us everything from light bulbs to the internet. Mastering the nuclear force gave us immense power, for better and for worse. Now, as we begin to touch and measure zero-point energy, we stand on the precipice of another potential revolution. What could we do with the ability to engineer the vacuum itself? The possibilities, while still speculative, are mind-boggling and could reshape our world in the 21st century and beyond. One of the most immediate applications is in the field of quantum computing. The very noise from zero-point energy that proves its existence is currently a major headache for building stable quantum computers. The random energy fluctuations can knock a delicate qubit out of its quantum state, destroying a calculation. But by understanding this energy, we can learn to shield our devices from it, or even manipulate it to our advantage. Engineering the vacuum state around a quantum processor could become the ultimate form of noise cancelling, paving the way for the powerful, fault-tolerant quantum computers we've been dreaming of. Further down the line, the possibilities become even more radical. Could we harvest this energy? The amount of zero-point energy in the volume of a single light bulb is, theoretically, enough to boil all the oceans of the world. The catch is that it's a ground state energy, the lowest possible energy state. Tapping it is like trying to get power from a ball that's already at the bottom of a valley. However, by manipulating the vacuum, perhaps using cleverly designed Casimir cavities, it might be possible to create energy differences and extract usable power. It's a monumental challenge, but the payoff, a limitless clean energy source, would be civilization-altering. And what about space travel? Some theoretical physicists have proposed that by manipulating the vacuum energy, it might be possible to create a warp drive. The idea, popularized in science fiction, involves warping space-time itself, expanding it behind a ship and contracting it in front. Such a feat would require generating negative energy, something that the dynamic Casimir Effect hints might be possible in localized regions. While this remains deep in the realm of theoretical speculation, the fact that our new understanding of zero-point energy makes these conversations even remotely plausible shows how profoundly our worldview is changing. The void is no longer the limit. It might just be the means. We began our journey by looking into the empty space between the stars. We end it by understanding that this space is not empty at all. It is a vibrant, dynamic arena, filled with an energy that is fundamental to the cosmos. This discovery does more than just add a new chapter to our physics textbooks. It forces us to update our personal, philosophical map of reality. The universe is not a quiet, static place with occasional bursts of activity. It is a place of constant, underlying turmoil, a quantum storm that rages silently in every cubic centimeter of space, including the space inside you. This new perspective elevates our sense of wonder. It means the simplest patch of nothing is a place of profound mystery and potential. Every time we create a better vacuum, we are not creating an absence of things. We are creating a purer sample of the universe's fundamental substrate to study. The quest to understand zero-point energy is a quest to understand the very foundation of space-time. It connects the infinitesimally small world of virtual particles to the grandest questions of cosmology, such as the mysterious dark energy that is causing the universe's expansion to accelerate. Could this dark energy be a manifestation of the vacuum energy itself? We don't know yet, but the question is now at the forefront of science. The future of this field is an open frontier, and it's an invitation to everyone. It calls for the next generation of bold experimenters, creative theorists, and curious minds. The questions we face are some of the most exciting in all of science. What are the complete properties of the vacuum? Can we truly build technologies from it? Does it hold the key to unifying gravity with quantum mechanics? Answering these will require new ideas, new technologies, and a willingness to challenge what we think we know about reality. The journey into the emptiness has only just begun. So keep looking up, keep asking questions. The cosmos is full of surprises, and the biggest ones are often hidden in the places we least expect, not in the brilliant light of a distant star, but in the profound, energetic, and beautiful darkness in between. The universe has revealed another of its secrets to us, and with it, a new ocean of possibilities awaits. All we have to do is be brave enough to set sail.